And in fact, he's one of the people who are centrally involved at Los Alamos, and that's one of the reasons he came up here, was to prepare this via doing the bid for the recompetition for the next 5 years of the MMSC. In any case, as I mentioned, he was the grandson of James Chadwick, who discovered the neutron in 1932. And I also learned just talking to him today that he has a son who's a freshman in economics here at Cal. So the chain seems to be broken. So maybe we run into him, see if we can prevail on him to come over to the dark side and work with us in the non-proliferation business. Okay, let's do a brief recap of what we've done in fission and then go into a little more technical detail.
I don't think that's plugged into the, I don't plug it to the.
I could just use the button here.
No, it's
Oh,
connected to your laptop.
it's my, oh, of course, that's the problem. All right. Good. We talked about the history, both the experimental discovery, which was done by chemists, difficult business because so much of what they were seeing for many years could have been consistent with microscopic amounts of contamination, but the case was finally made. Lisa Meitner, who put together the first visual picture based on what's called liquid drop model. And what was seen in the way of two medium wave nuclei that emanated from uranium-235 after the absorption of a slow neutron. And then Szilard was already spring-loaded. He had actually conceived in theory about the possibility of a chain reaction without knowing exactly what that reaction would be that would give you two neutrons out for every neutron coming in, or on the average at least more than one neutron, to give you an exponential and immediate increase in the number of neutrons and the release of energy. Later on, when we do a sanitized discussion of the sort of the primitive elements of nuclear weapons physics, we're actually going to go through the exercise of calculating how fast it takes for a chain reaction to consume the entire fissionable amount of material in a Trinity type nuclear weapon. It is astonishing. It is astonishing how fast it comes out. In fact, Edward Teller, I don't know if those of you who are weapons junkies may know what's now been for many, many decades already, a technical unit of time in the nuclear weapons business. You must know.
A shake.
A shake. How much is a shake?
Isn't it 2 nanoseconds?
10 nanoseconds.
10 nanoseconds.
You might say, why was it called a shake? It was a comment that Teller made when he said that once the chain reaction takes off, it's all over in 2 shakes of the lamb's tail. It really is very, very fast. All of the, business of the detonation of the high explosives and the compression of the primary fuel takes place on the scale of tens of microseconds. But once you get criticality there, prompt criticality, the exponential consumption of the fuel and release of energy is just blindingly fast. I think it's 10 to 100 nanoseconds, and this massive amount of energy is released. Unstoppable with that. Okay, we talked about how it was determined that 235 and 238, well, it was known that there were 2 isotopes here, but which was the fissionable isotope. They did an electromagnetic separation of the 2 that separated the beams of these 2 species just enough to be implanted on a foil that would take to a postcard, put in an envelope, and then mailed to California, where they irradiated each of the 2 halves of the foil separately. And thank heavens, discovered it was a minority component of uranium that was fissionable. and we talked about Seaborg and plutonium here. So here's the basic picture that LIGHTR had. A slow neutron is absorbed by uranium nucleus. It can be a fast neutron as well. This now has an excitation energy which is great enough to get it over some kind of potential barrier to go from the shape of a spherical or slightly elongated nucleus to the fission point. Once the nucleus becomes elongated sufficiently, you can see exactly what's happening. This is a highly charged object, and you have now sort of two kind of proto-daughter nuclei separated. You have an enormous sort of collective Coulombic repulsion between the two, and then this thing elongates, snaps, think of like taffy, and then the Coulomb force pushes it down the 1/r potential, picking up an enormous amount of energy. And what one is left over with are two daughter nuclei, now also hot, in an excited state, and some prompt neutrons were emitted from the fission, what's called the neck, fission point of that. There can be neutrons which are emitted while if the neutron, if these two nuclei, daughter nuclei, are left in an excited state above the separation energy, then you can actually get further neutron decay here from the daughter nuclei themselves. Okay, we've seen this now at least 3 times, and I'm going to show it a couple times more because it's very, very important. This is the curve of binding energy, the average binding energy per nucleon across the entire table of the isotopes. It has a maximum in the iron group region, which means its nuclei are less bound on the average for nuclei lighter than that, and they're actually less bound as you go up in atomic mass. And that is what where you get the profit, so to speak, of energy. I can now take a heavy nucleus here, compare it to the sum total of the masses of the two daughter nuclei. They are more tightly bound, therefore they're lighter. This is less well bound. Only got on the average of about 7 MeV binding per nucleon. The daughter nuclei will have on the average of something around 8, which means to say you're going to gain about an MeV per nucleon. This whole process of splitting it in half. And as I think I asked you, and some of the guys answered it very well, 200 and something times an MeV is 200. Okay, so that's exactly the amount of energy that you get out. Okay, same thing. Okay, here's the budget, the energy budget that comes out of nuclear fission. Most of it, sort of 3/4 of it or more, comes out in the kinetic energy of the fragments themselves. And as you know, if you've done some nuclear physics in the past, these are highly charged ionized ions, very, very heavy nuclei, recoiling with a lot of kinetic energy. They are going to cause a massive amount of ionization, energy loss, and therefore they lose a lot of energy very shortly, and they're going to stop in a very localized region and deposit the heat associated with their kinetic energy very, very locally to where the fission takes place. You get, on the average, depending on the fission of the species, depending on the excitation energy, depending on the initial energy of whatever came in to strike the thing, about 5 MeV total worth of neutrons in about 2.5 neutrons. So there's about 2 MeV per neutron coming out. I think I show this later, but maybe not. But let me just draw a picture of it right now. If I make a plot of the energy of the neutrons coming out from slow neutron-induced fission, And then here's simply the probability of that energy. And this is, we'll do this in terms of a log plot. This is a linear plot. You have something called 5 MeV. It's called the Watt spectrum. And it's on a log plot. Let me see if I can sketch it. So it kind of comes down. If I do a linear plot, if I draw a linear plot, so on the average energy is itself of order of an MeV, I don't have a precise number. But with the long tail, you actually find that you will find some neutrons even coming out with more than 10 MeV. Okay. But very few of them are intrinsically very slow. There are reasons why in reactors that one wants to moderate them with use of paraffin or water or carbon, whatever like this. That will, but the spectrum coming out from prompt fission is actually what's called a fast spectrum. You get gamma rays immediately, not very few from the actual compound nucleus itself, but once you the nucleus scissions into two parts, you have a lot of intrinsic energy, excitation energy in the two daughter nuclei, and they will if there's a neutron to be emitted, it'll come out first. Otherwise, it'll kind of rattle down, emitting a lot of gamma rays. There'll be typically about 7 MeV in the prompt gamma rays. You'll see prompt gamma rays, and then you'll see fission product gamma rays, so a total of about 14. Once the daughter nuclei begin to land on the valley of stability, then of course these things are unstable, and then they'll begin to beta decay down. We'll take a look at the chart of the nuclear in just a second. And you'll get about 5 MeV worth of betas. And then not useful because they interact so weakly, they just fly out, but you'll see on the order of about 10 MeV of neutrinos. So you get a total of about 200 MeV total energy. Okay, so now here's the story. So I hope you've played with the NNDC interactive chart. It's a lot of fun. You can learn some interesting things. Here are your fissionable nuclei. If I ask you, where do, when this thing splits into two nuclei, where do they land? Who's got a good answer? Typically, where do they land? Almost invariably, where do they land?
On the other side of the valley stability,
Oh, where's the other?
that's left,
Oh, up here?
somewhere left.
Oh, that's the first time you've missed a question this semester. You were on a roll.
I didn't say it.
Where? If the left is not the right answer, the right answer is right. Now, here, look carefully. This thing bends. It's kind of bowed. So if I now split this thing into two, now event to event, you never get the same partitioning of the two fragments. In fact, you get thousands of combinations. But on the main, what happens is if I draw a straight line, this thing is very neutron rich. Okay? It's got 92 protons and 146 neutrons. It's very neutron rich. And therefore, when I divide this into two, on the average, they're going to be here on this side of the valley. Remember, think about this thing as a valley. This is the bottom of the valley. And then what you have in energy space is a steep wall like this. So where they land is also going to be neutron rich, but they're also going to be up on the side of the valley, and therefore, by beta decay, they're going to end up skiing down over a period of time down to the bottom of the valley. You saw that. I'll show you this picture again about what the valley looks like when I deviate from the what is normally the natural isotopic ratio of neutrons to protons. By the way, why does that valley of stability bend over? Why is the chart of the isotopes bending over? For very light nuclei, it's perfectly happy being 50-50 protons, neutrons. Oxygen 16 is 8 and 8, calcium 40 is 20 plus 20, helium is 2 plus 2. When I get to very heavy things, it's preferring this nuclei be neutron rich. That's because, yes, or why?
Because the distances, the positive charge of proton.
Yeah, there's a penalty, there's a price being paid for being charged. I can write down, this is a little bit of a deviation, let's see if I can remember it here. One of the earliest mass models, and this is what Lisa Meitner had in mind here, it was called the Weizsäcker, Carl Weizsäcker, see it here. Mass formula, also known as, there's sort of an analogy. Speed it up here. Liquid drop model. Which is actually extremely good. And in fact, on the average, the mass of the nucleus, I'm doing this now from memory. Well, the lowest order, it's the number of neutrons times the mass of the number of protons to the mass of the proton. Number of neutrons, which is A minus C times the mass of the neutron. So you also have a volume, that's the leading order term. You have a volume term, which is going to go like A. And this coefficient here is coefficient for the volume. And what sign term do you think C is, a positive or a negative number? Is the nucleus bound? Yes. Therefore, that number is no. This is the mass. The mass is less than the individual constituents. This number is actually negative. But it's not pure volume. What else does a finite object have? What has energy? Surface. Okay. There's a surface term. This goes like the radius squared, the 4 pi r squared. And how does this contribute to the binding of an energy, mass of the student? Do surfaces increase or diminish the total binding energy? Decrease, right, so it is positive, okay? So nuclei that are lighter have more surface to volume ratio, on the average are less bound, they're less stable. You then have a term that goes, which is the Coulombic term. And was commented in the back, it's going to go like z squared over the radius, so it's 8 to the minus 1/3, average distance of nuclei one to another. And that is also going to be a negative contribution, a positive contribution, because it's trying to push things apart. So it's not helping. It's actually a unbinding effect. It's increasing the mass and therefore decreasing the binding. You have a symmetry term. See, this is a great mystery itself. You might say, well, I can understand why nuclei may want to be more neutron rich as they get heavier, but there's a mystery here you never asked about. Why do they want to be equal neutrons and protons in the first place? See, putting aside the Coulomb force, they do want to be equal number of neutrons and protons. This actually is a consequence of actually quantum mechanics, that you actually have to fill up the register, fill up the stack of neutrons and protons individually. They're fermions, spin-half particles, and there's a penalty to be paid if they're unbalanced one way or another, 2 neutron rich or 2 neutron poor. So there's a symmetry term here which prefers that z minus n or a minus 2z squared. And this thing also is an unbinding term. In other words, if you get out of whack, back. This thing also is a penalty. So this also increases the mass and decreases the binding. And then there's one more term. Which is called the pairing term. And it tends to, and it is positive if you have, let's see if I remember this correctly. If you have odd, no, that's right, yeah, so. Okay. Odd even is 0, and even is nice. Even nuclei tend to be tightly bound. So that's a small effect of the order of an NDP. Anyway, bit of a digression. Now, this is just a fact of life, but it's a mystery. You might say, well, a nucleus splits in half. Why doesn't it split 50-50 and give you a nucleus right in the middle? It doesn't. It tends to be extremely asymmetric. That's a log plot. You see, it dramatically favors having something in the vicinity of 90 plus or minus 10, and something around 140 plus or minus 10, something like that. Again, event to event, you can get all kinds of crazy combinations of isotopes that add up to the original one. But it is very, very, very rare you get a symmetric fission. In fact, symmetric fission happens at about the percent level that it splits exactly into 2 fragments of about half the total mass. And then, as I mentioned, Oh, okay. As I mentioned, once you land on the side of the valley, it needs to ski down. And let me show you that right now. This is a better behaved picture of a crosscut through the Mass 137 system. This very nice parabolic curve is exactly that term. It's the symmetry term. The ones I showed you for lighter nuclei tend to be a little bit oddly shapen. They were valley, but they tend to be a little bit more linear or whatnot. This is a very nice kind of quadratic thing that is just reflecting the fact that nuclei don't like to be too out of whack between protons and neutrons. Although, if you throw in this phenomenon, the fact that charged nuclei tend to drive that stability more neutron rich. Anyway, here's, you can see what happens if I form, this is the neutron rich side, tin 137 is so high, is so up on the side of the valley of stability, things which are very energetically out of whack here will decay quickly. There's a big difference in energy between tin 137 and antimony 137. And so this lasts 190 milliseconds. From here to here is 450 milliseconds. Sort of tellurium to iodine 137 is 2.5 seconds. Iodine to xenon 137 is 25 seconds. Xenon to cesium is 3.8 minutes. And here's the bad actor. This is the kind of thing you worry about if you've seen the movie Chernobyl and so forth. It's the things which are not short-lived, not the things that are long-lived. It's the things that are kind of in the middle that are really problematic. This lives 30 years. These guys, you don't have to worry about because 10 half-lives is a couple of seconds. They're gone. It just doesn't matter at all. Something like uranium that alpha decays with a 4.5 billion half-life, you don't have to worry about it at all because the half-life is so long, it never decays or decays very rarely. I would not recommend you use it as a coffee table ornament, but you don't have to worry about it. It's these guys that have lifetimes comparable to human lifetimes, years, tens of years, maybe thousands of years, which are long enough lived that you can't wait them out, but are short enough lived that, lambda, the decay constant, means that a lot of radiation is coming out. What are the bad actors? Let me back up. Okay. Now, where do these things come from? We're actually going to have a talk on fuel cycle. We'll talk about two things which really enter, really are the crux of the non-proliferation mission, like what are the two options that countries have if they wanted to start a program, a nuclear weapons program. And by the way, one of them is something you would need to do to run a perfectly legitimate civilian program. That makes things complicated. How do you dig out that 0.7% of uranium-235 out of natural uranium? And then you also, to make a uranium weapon, plutonium-239 is produced as a it's cooked inside fission reactors. Here, you say 238 uranium absorbs a neutron, it becomes 239 uranium, and then undergoes two beta decays, 23.5 minutes, 2.36 days, and you end up with plutonium-239, like that. And then both fission upon capture of slow neutrons. So we'll talk about that. In the case of uranium, there's 4 ways of doing it. There's electromagnetic separation that Ernest Lawrence first did. It was done on a small scale. And the first demonstration was done, when you're driving up University Avenue, you see that old dome. It's a National Historical Landmark. I think it's red. That contains the advanced light source, a modern facility. But they kept that building because it is a very famous building. It's a National Historical Landmark. in there was the 184-inch cyclotron that was built during the war. And Ernest Lawrence and his team of graduate students and researchers and engineers actually developed a process for doing, just like near the spectrograph, electromagnetically separating 235 from 238. Not the best way to do it, but of course, in fact, a lot of uranium was made during the war at Oak Ridge there with the electromagnetic separation program there at the racetrack called Calutrons. Calutron, Cal stands for Cal, right? It came out of University of California. The concept for it. Gaseous diffusion, because diffusion through permeable membranes has a very slight dependence on the mass at a given temperature. Now, what is the tool of the trade for all modern programs, which is the centrifuge, and we're going to have a lovely talk by Scott Kemp, who's here with the Goldman School on sabbatical this spring from MIT, and then we'll talk about laser isotope separation, a major program that was developed many years ago at Lawrence Livermore National Lab. Now, that's something that's only done by very sophisticated countries. Actually, that's a very high-tech way of doing the separation. This is chemistry. I am not a chemist. I even asked Scott Kemp, and Scott said, I'm not a chemist. But I will get Rebecca Abershell here to talk about how the chemistry is done to separate plutonium from spent fuel. Okay, we mentioned this. The bad actors, cesium, 30 years, iodine, strontium, close to 30 years. And those are the ones which are very, very problematic. Okay, I think I didn't want to finish. What? It's up to you. What do you think? I've actually come to the end. I'm ready to go with the next segment. Take over here. Okay. Oh, it doesn't matter, doesn't it? Okay.
I'm sorry, this is a little disjointed, but Mr. Van Gogh continues with his material, and then I continue. So last time I went through rather quickly a sketchy summary of nuclear arms control in the United States and the Soviet Union. I want to go through it in a bit more detail today, from the SALT I agreements to the New START Treaty, which is the subject of your project. And then on Wednesday, I'm going to go over the highlights of the key points that you should know about in the Kaplan book, which go back from the 50s up till the late 60s. Okay. So first, SALT I. Now again, it's hard to convey to you what a difficult relationship the United States and the Soviet Union had during the Cold War. I have a couple of anecdotes to relate in my personal experience. This was actually a little bit before I got into this business. I was a graduate student at this time, and about a year and a half later, I was a postdoc at Harvard, where I met a couple of members of the U.S. SALT I delegation. And that was my first personal experience to understand how the negotiation process works, how the interagency process works, and so forth. This is Jimmy Carter. I'm sorry, no, this is not Jimmy Carter. May 72. That's not right. It's the wrong photograph. Sorry about that. That is Jimmy Carter. And this is Stig Brzezinski, the National Security Advisor to Carter. And this is Harold Brown, the Secretary of Defense under Carter. And this is Cyrus Vance, Secretary of State under Carter. And this is Gromyko, the prime minister of the Soviet Union for 35 years under Brezhnev and his associates. So this is actually a photo of the start of the SALT II signing, which is in 1979. Sorry, it's a mistaken photo. Going back to this agreement, 1972 was an election year. And you may or may not be aware, presidents like to do things during election years to help promote their election chances, re-election chances. So you'll see something by this president, I'm sure, besides hiring people, he's going to try to do some other things to promote his re-election chances. In 1972, Nixon was president. This is Kansas SALT II. In 1972, Nixon was very concerned about his re-election chances because Vietnam had been very unpopular, and Nixon had said he had a secret way to end the war and never revealed it to anybody, including himself. So there was a lot of anxiety in the White House about Nixon's re-election chances. The Democrats had looked like they were going to nominate a moderate named Ed Muskie, who was a senator from Maine. And there was actually a dirty trick played on him. Look at the dirty tricks. Dirty tricks is where you try to do things to screw up the candidate so they self-destruct. And he was given some questions and comments at a press conference where he started to cry. And this actually destroyed his candidacy. People thought he was too weak. Instead, the Democrats nominated someone from the very far left. Might sound familiar to you in current times. And this was George McGovern, who was a senator from South Dakota, who was actually a bomber pilot during the Second World War, but had moved very far to the left as a senator. And Nixon totally destroyed him in the presidential election. Someone, an unpopular president, destroyed the far left Democratic candidate. I believe McGovern got one state, and Nixon won 49 states. So if you're thinking about your candidates, you might keep that in mind. This is not a far left country. We don't tend to elect hyper-liberal presidents. Even Obama ran as a moderate, not as a as part of the effort to promote his re-election chances, Nixon was very keen on signing an agreement with the Russians, which was his first SALT I peace authorization talk. It had two parts. First part was an interim offensive agreement, and the second part was the ABM treaty. This agreement lasted only for 5 years. It froze deployments on the launch vehicles. Most of the focus of nuclear arms control has not been on the weapons, they've been on the delivery vehicles. These are the US IBMs 1054, which is the total number we had deployed in the Dakotas and elsewhere in the center of the United States. The Soviets had already deployed more, 1,618, so they agreed to freeze it at that level. But notice that was a big disparity. Usually a third more weapons that the Soviets had in the United States, which caused a huge uproar in the US Senate. And a key figure at that time was Senator Scoop Jackson. Anybody ever heard of Scoop Jackson? Nobody ever heard of Scoop Jackson. He was a prominent senator from Washington State who ran for president in 1976. And he insisted that an amendment be attached to the treaty that determined that in the future there had to be numerical equality in all major categories in any future arms control agreement. The United States could not tolerate, whether they're militarily meaningful or not, we could not tolerate to be numerically inferior to the Soviet Union in any category of weaponry constrained by non-control agreement. Besides the ICBMs, there was a limit on submarine launch ballistic missile launchers. The U.S. had 44 SSBNs, those are subsurface ballistic nuclear submarines, and they carried a total of 710 SOBM launchers, whereas the Soviets at the time already had 950. Again, at a substantial numerical advantage. This, I cannot convey to you the animosity this generated in the U.S. Senate that we were signing agreements codifying numerical inferiority. So it was intergalactic in scope. But Nixon wanted to do it to help his reelection, and he was able to lobby it and get it through. So this was the interim offensive agreement, which lasted 5 years and 77 had lapsed. Any questions about this? And then I have the wrong photograph here. So the group here would have been, if this was correct, this would have been President Nixon, and the National Security Advisor was Henry Kissinger. The Defense Secretary was the senator from Melvin Laird, senator from Wisconsin, was the Defense Secretary. And this was largely an effort done by Nixon and Kissinger without the involvement of other key officials. But Brezhnev was the signature of the SALT I agreements also. He had overthrown Khrushchev in 1964. Yes.
So SALT one had no mechanisms for how many warheads were inside.
Correct. Correct. And the reason for that was the U.S. at that time secretly was deploying, at least we thought it was secret, except the Soviets had penetrated our classification system to know all about it. We had tested and deployed multiple independently targetable range vehicles, MIRVs, MIRV. The Soviets did then, shortly thereafter, they also deployed MIRVs. The other component of the SALT I treaty was the ABM treaty. And notice that this agreement, first thing I mentioned to you was an agreement, right? So an agreement is an executive agreement, which means it's something that the president signs, but the Senate doesn't approve it, doesn't ratify it. A treaty is what is ratified by the Senate, 2/3 vote. So the interim agreement was never, the Senate insisted on approving it, but they under law didn't have to approve it because it was an executive agreement. But the ABM treaty had to be ratified by 2/3 of the Senate, which it was. And that greatly constrained ABM deployment. Anti-ballistic deployments. Just 2 sites with 100 interceptors each, one for the national capital, so the Russians had a site around Moscow, and the US had a site around Washington. And then we each had an ICM field, at least 1,500 kilometers from the national capital, where we could also protect them with the ABM system. This was a treaty of permanent duration, but again, like many other treaties, the parties to a treaty have the right to withdraw from the treaty if its national security is threatened. And later in 2002, 30 years after the signing of the treaty, and ratifying the treaty, President George W. Bush claimed that the ABM treaty was threatening U.S. national security because it constrained us from deploying ABM systems, which we needed to deploy defend against targets that would be aimed at by North Korean and Iranian offensive systems. And we wanted to deploy limited ABM systems in Alaska and California, as well as defend U.S. targets from limited Russian missile attack. So, now, the ABM treaty was always a treaty of tremendous controversy, even though the Senate approved it. There was always this very vocal and powerful and distinct minority that claimed no arms control agreement with the Soviet Union is worth the paper it's written on, because they're only interested in cheating. And the only kinds of arms control agreements you can get that are worthwhile are with friends like the British. We don't need any treaty. So critics like Richard Pearl, who was an advisor to Sue Jackson, said arms control is either worthless or dangerous. And so,
Yeah, I have a question about Abraham treaty. So that treaty is based on not only the balance of threat, but also the balance of vulnerability. Some historians said the U.S. will withdraw from the Abraham treaty in 2002. And that implies that the U.S. is moving away from the policy of balance of threat. So U.S. ends the age of vulnerability, and it is moving forward like really level.
well, I think that's probably right. I think the George W. Bush administration, which included many people, including John Bolton, you may have heard of him. Are any of you following what's going on with the presidential election at all? Any? Not really. I really have seen no idea what's happening. Never heard of any of the people when you fought that. So there's a presidential election coming on right now. We have a president called Donald Trump, and he's been involved in some interesting activities called the impeachment process. Third time in American history, the president's been impeached. And there was a deep, bitter fight going on, which you may be totally aware of, between the Democrats and the Republicans over this election. And Bolton, who's a key figure in that business, we'll talk about further, was a figure in the George W. Bush administration, deeply anti-arms control. You know, his religion was against arms control. And he believed that we needed to get rid of these systems so we could get rid of the agreement so we could deploy missile defense systems to protect against limited North Korean or Iranian attack. That we were vulnerable to North Korean or Iranian attack. And not only we were, but our allies, the South Koreans, the Japanese were vulnerable to North Korean attack. The Europeans were vulnerable to the Iranian attack. Well, to get into a lot of the details on this, I happen to believe that they were correct, that there's no doubt that those targets were vulnerable to attack. Whether it was worth to give up the Abraham treaty to do that, that's another question. So, again, 1 second. So the SALT I agreement had two parts: an interim agreement on offensive arms for 5 years, an ABM treaty of unlimited duration that lasted for 30 years, for George W. Bush exercised our right to withdraw. The U.S. did not abrogate the treaty, which means to violate it. We didn't abrogate it. We exercised our right to withdraw. Yes.
What's the process for withdrawing from a treaty like this? Like, can the president make the decision to withdraw by himself?
Yes. Yes, there's no Senate vote.
One more question. So what, like, you mentioned the difference between an executive agreement, arms agreement, and an arms treaty.
Right.
And because the Senate's involved in the treaty, it seems like it's more binding. But like, what is the practical difference?
Well, the treaty is it's a firm commitment under international law. Yeah, maybe I did mention, this. There are three parts to an international agreement. The first is the duly authorized representative of the head of state has to sign a piece of paper. Like Carter was signing. That's a signature, and you are a signator to the treaty. Then you have to go through whatever the government's policies are for ratification. In the Soviet Union or Russia, the Duma, which is the parliament, just agrees to whatever the executive says. It doesn't matter what it says. It's like the Republicans with Trump. It doesn't matter. It's irrelevant what he says or does. They support him. That's what the Russians, that's what the North, you ever seen the North Korean parliament? Is there any opponents to get going on there? No. Any opponents are dead. Okay. So if the US Senate approves by 2/3 vote to ratify the treaty, then the treaty is ratified. Then, in the terms of the treaty, it explains where physically the treaty has to be deposited. Where is it physically placed? It's usually placed in the national capitals of the signatories of the treaty. In this case, Washington and Moscow, and also usually at the United Nations, maybe in Geneva. Once it's signed, ratified, and deposited, when it's deposited, it enters into force of EIF. When EIF is complete, it is binding on the parties. There's none of that within the executive agreement. I'm glad you asked that because I have to clarify. It's important to you should be aware. Any other questions or comments?
The SALT one was the first of this thing we did. What was placed in force at that time in the way of verification?
Yes, so the US had, it didn't really specify verification much in SALT one, that came in later agreements. But we had developed by that time, satellites, first satellites had been put into place. And we also had U-2 aircraft and advances to the U-2. And we also had electronic eavesdropping, and we also had human intelligence. So all four measures are used to ensure that the Soviets are complying with
But the only place we would be looking to see the submarine component is
Submarine.
reports.
right.
So,
Except that we had other sources of information about it. There is an intense, indefinite espionage game going on between the United States and Russia, even if this president believes Putin doesn't believe our 17 intelligence agencies. We don't know anything about that. In 2016, we had a presidential election when Trump was victorious. And in that election, there were interventions by cyber and other elements to influence the outcome of the election. And we have 17 intelligence agencies that concluded that the Russians and only the Russians were involved in penetrating our electoral system and distorting the votes. Trump has rejected that because he said that Putin said they didn't do it. And instead, he has concocted this notion, which is Russian propaganda, that the Ukrainians have been involved in this. This has to do with the fact, I don't want to get too far in, but you need a ton of background. You don't have any knowledge or interest. This is a big deal, even if you're totally unaware. Okay. Kissinger, this is Henry Kissinger. Kissinger is now, he's born in 1923, so he is now 90, in March, he'll be 97. 97 years old. And he made a famous statement, arms control is not about arms control. And what he meant by that was that the US was trying to promote interaction with the Soviet Union to foster human interaction with them, to get them to be exposed to American ideas and American thinking. The Soviet Union was completely isolated from the rest of the world except for their allies at this time. I'll give you a couple of quick anecdotes. In 1974, 2 years after this was signed, was my first trip as a young man to the Soviet Union in 1974. And a couple of quick anecdotes. There were basically almost no scientific, absolutely no economic, and absolutely no military context of any kind between the Soviet Union and the United States. The Soviet Union was totally isolated except for its allies in Eastern Europe and the North Koreans and the Cubans and the Vietnamese, its communist allies. Before I went on this trip, I was told by an MIT professor who couldn't go, who had been on other trips, to look out. Did I tell you this story or not? To look out for the grand piano in the hotel where we would be staying. As I told him the name of the hotel was called the Lucia Hotel. It's a gigantic hotel with 4,000 rooms. It could easily be divided up into a prison camp if it was to be shut down. And when I got to the hotel, there was this grand piano in the lobby, a huge grand piano. And on top of the grand piano was a man sleeping in a sleeping bag. He never told me what to do. He said, watch out for the grand piano. So when we got to the reception desk to check in, I was with 4 of the people from the US delegation. They said everybody is okay except for this one man. Unfortunately, it wasn't me. There's another MIT professor, very famous, George Raftins. And they said, we don't have any room for you, Professor Raftins. Today, this is 4 o'clock in the afternoon. The group said, you see the piano over there? You see the man sleeping on that piano? Well, 11 o'clock at night, he has to leave to take a train to Kiev, to Ukraine. And once he leaves, you can sleep on the piano. And then in the morning, we'll have a room for you. So I don't make, I'm not making this up. Also, when you fly on the way over, I took a flight to Stockholm, from Stockholm to Moscow on Aeroflot, which is the Russian airline. It looks like they have pedals and bicycles in the front to keep it afloat. Very primitive aircraft. And I remember being on the airplane and I was with this very distinguished man, Herbert York, all knows all about. He was first director of the Lawrence Livermore National Laboratory, member of the Manhattan Project. He couldn't be in the trip. We went to Washington first and met with Kissinger and met with Schlesinger, Secretary of Defense, for briefings before the trip. And I was there to meet York in Stockholm, tell him a little bit about what happened in the briefings. And talking to him, and all of a sudden I had a sharp pain in my head. I'm sitting in the airplane, sharp pain in my head. What happened was the flight attendant, who was a woman who looked like she was a lineman for the San Francisco 49ers football team, was throwing boxes. These were box lunches to the passengers, walking down the aisle, throwing them, and she smacked me right in the head with this luncheon. My very first welcoming to the Soviet Union. After we got settled in the lobby with my friend going to the piano, we agreed to meet to go downstairs. There was a restaurant about to leave. And these others had all been to the Soviet Union a number of times. I had never been there before. But I was a junior person on there. And the waitress gave us a menu, which was this gigantic menu. It had like 25 appetizers, 40 main dishes, and 30 desserts. But the items only had a few where there were numbers next to the letters. And it's Cyrillic, which I couldn't read much Russian. And I said, what does that mean? We got all these dishes Only a few of them have numbers next to them. And they said, the menu is the aspirational list of what they would like to be able to serve. The numbers, or if they had that in stock and served it, that's what they would cost. It would cost. And then the waiter will tell you what they have. So for example, there was 30 desserts, 7 had prices next to them, and the waiter said, vanilla ice cream, that's it. So this is, to give you a little feeling for what the Soviet Union was like in the 70s. It was like being on Pluto. There was not a single experience I had that had any relevance to what it was like being in Moscow. I have many other examples I want to give you.
You've been to Russia?
So, oh, there's the Garcia Hotel. Yes, this was the hotel, right? Well, it's not that man, so, I see it's gigantic hotel. And they had the doors that could close and close off the, wings of the hotel. Actually, when you took the elevator up to your floor, whatever floor you were on, when you got out, there was a lady sitting on a stool. She was called a key lady. And she gave you a key to your room. She was there to keep track of you if you walked in and out of the room. If anybody else walked in and out of the room. You were constantly being monitored. Of course, the telephone was everything. Monitored. You may have heard of, you haven't heard. There's a whole thing about Trump having been in the hotel in Moscow with prostitutes. And he was very angry at Obama. And it claimed that the room they gave him was the room that Obama was in. And Trump arranged to have 2 prostitutes come up to the room and urinate on the bed, because this was the bed that Obama had slept in. And I mean, not believing a word I'm saying it. I'm telling you this is true. So, and of course this was taped, videotaped by the Russians. So one of the issues, why is Trump so supportive of Putin? Because he's got evidence of the meeting with prostitutes urinating on the bed. And this means 0 to you. It's quite important. Okay. So what was Kissinger talking about here? He was saying arms control is about a process to interact with the Soviets so that they begin to have ideas other than the doctrine they've been absorbed to accept. And that over time, this might lead them to moderate some of their virulently anti-American policy. Any questions about this? How many of you have been to Russia? Just the one. After Nixon was forced out under Watergate, Ford became president. Kissinger had the policy of the U.S. to improve relations called détente, and Ford was persuaded not to follow the policy of détente. He thought that he would not be elected in his own right if they followed détente. Ford later said that this was his biggest mistake. If they followed détente, so he would have been elected. 1976. He lost to Carter. Carter became president. That's where you saw that he sold 2 treaties, the photograph 4. Sold 2 treaty was signed in June 1979. There's a follow-on agreement to the Sold 1 agreement. Established numerical equality of the weapon delivery systems. So this comported with the Jackson Amendment. Jackson said, in the future, no agreements will have numerical inferiority. It limited the number of deployed MIRV missiles. Carter wanted to submit the treaty to ratification of the U.S. Senate. I was going to do so in the fall of 1979, 3 months after the treaty was signed. But in December 1979, there was a surprise Soviet invasion of Afghanistan. Soviets had built roads. So Afghanistan is adjacent to the Soviet Union. There were roads that allowed Soviet tanks to enter Afghanistan from the Soviet Union. And this was a huge surprise. The U.S. intelligence did not pick it up. And Carter was completely flabbergasted by this. So it was very damaging to Carter. He was viewed as extremely naive, not understanding who was dealing with the Russians. So instead, Carter withdrew the SALT II treaty from Senate ratification. He stopped the process, so the SALT II treaty never came up for ratification and never entered into force. But yes, there was a.
Why did the Soviets invade Afghanistan?
So they invaded Afghanistan for several reasons. They wanted to move more directly into the Middle East. This is a path to that, and to the oil fields in the Middle East. And it was thought that Brezhnev thought that Carter was naive and could be taken advantage of, as Khrushchev thought JFK could be taken advantage of. This goes back to the inherent view of Kennan. So communists are inherently expansionist. They're there every day figuring out how to expand beyond their borders, every single day. Yes, sir.
That's how we think we stuff that you guys put. That Russia number or the action of the Soviet number.
It actually led, I think, to the U.S. Reached the same limit as the Soviet Union.
So what was the benefit for Soviets?
So they thought that if, good question, it's, the Soviets thought that if the U.S. signed the SALT II treaty, that the numbers actually themselves didn't matter much. But this would constrain U.S. R&D development of new weapon systems, which the Soviets would continue to do secretly.
So why did the Soviets, or I guess, did the Soviets dislike arms control more than the United States, since they were pouring a much greater portion of their economy into defense spending? Like, wouldn't it be in their best interest to limit the United States? So
Well, because this didn't necessarily constrain a lot of their weapon systems, constrain, long-range missiles, constrain their tanks, constrain all key elements of Soviet military power. The nuclear component is only one small component of the intense military competition in the US. Maybe the most important, most disruptive, but it's only one component. After Carter withdrew the SALT II treaty from ratification, he then was confronted in 1978 with the Iranian crisis and 1979 with the hostage crisis, where the U.S. diplomats were put under house arrest by the Iranians. 52 U.S. diplomats were under house arrest, 444 days by the Iranians. This was the start of the intense animosity between Iran and the United States, which is to this moment. Carter tried a separate rescue mission to get the hostages out, and it failed. There were 8 helicopters brought into the desert in Iraq. 2 of them crashed. There was a windstorm, sand blew into the gears of the helicopters. It was sort of like it was like the Iowa primary people involved in planning this. and it was humiliating for Carter. This was in May of 1980, the election year. So presidents try to do things in the election year to improve their chances. This destroyed his chance. It was humiliating. And in 1980, in the November election, Ronald Reagan, who was thought of as an extremist, completely uninformed, a movie actor, no knowledge of almost any of this stuff, totally destroyed Carter in the election. And he came in with a very strong anti-Soviet position. And that lasted the entire first term of Reagan, 1981 to 1985. But a couple of Soviet leaders had come and gone, had died. Brezhnev had died, and Dropov, the head of the KGB, had died, and Chernenko, whose chauffeur, had become president. He had died. And but then in 1985, a very smart man, Mikhail Gorbachev, became president. And Reagan clicked with him. Reagan had meetings with him and got along well. And Gorbachev had an interesting idea. Gorbachev thought that a lot of this competition with the US was dangerous and unnecessary. Gorbachev thought the communist economic system was the correct system, was the preferred dominant system, but it didn't need to require an oppressive political system. So Gorbachev loosened the bounds of the Soviets on the countries of Eastern Europe. You've been to Poland, Hungary, the Czech Republic, any of these countries, it was like when I was in the Soviet Union in the 1970s. Zero freedom. If you want to go from place X to place Y, to fill out forms to get government approval, do that. Gorbachev was going to relax all those because he didn't think they were necessary. When he relaxed them, the people fled and left the country, and including those from East Germany who climbed over the Berlin Wall and basically led to the collapse of the Soviet Empire. But before that happened, Reagan and Gorbachev reached a major nuclear agreement, the Intermediate Nuclear Forces Treaty in 1987, which prohibited short and intermediate range ballistic and ground launched cruise missiles directed between 500 to 5,500 kilometers. And this lasted from 1987 until just last summer. When I was in government under Obama, 2009, 2010, we had information that we thought the Russians, not Soviet anymore, the Russians, were violating the INF Treaty. They were testing and beginning to deploy a new system, the SSC-8, a ground-launched cruise missile with a range of 2,500 kilometers. That's a violation of the agreement. Obama chose not to press them on it. This is an interesting example. One of the only counterexamples to Trump's pro-Russian policy. He actually permitted his Secretary of State and Defense to raise this with the Russians and to say that we were aware of the SSC-8 system, that it was being deployed as early as 2017, and if they didn't stop it, this would lead to the U.S. to withdraw from the treaty. They did not stop it. They denied the existence of these systems. We had all kinds of satellite photographs, electronic information, stack of information that's thick about it. And finally, in August of 2019, just last August, under Trump, the U.S. withdrew from the INF Treaty. And now the Russians have withdrawn from it. The INF Treaty is defunct, no longer exists.
So if the INF Treaty was actually a treaty, based on what you said earlier, it falls under international law.
Right.
If there was strong evidence that Russia was violating this law, why, what did the UN do in response?
There's nothing you can do because any meaningful action in the United Nations has to be approved by the UN Security Council. There are 5 permanent members of the Security Council, one of them is Russia. Russia is not going to approve a punishment against themselves. So they would veto any action taken by the Security Council. So the US never even brought it up. So this is an important, very important, this is considered one of the highlights of Reagan's détente policy with Russia, but now it doesn't exist. In the meantime, after Reagan left power in 1989. 1988, there was an election and George H.W. Bush, the father of George W. Bush, became president. And in 1991 and 1993, he approved George H.W. Bush 2 follow-on agreements, strategic arms reduction agreements. These are actually conceptually started by Reagan, but they're agreed to by George H.W. Bush. And here are the details. I'm going to run out of time, so I'm not going to go into this much. Start 1, limited. The warheads, here's a limit on warheads. 6,000 warheads of 1,600 ICBMs bombers. A major reduction in the number of deployed strategic nuclear weapons. Remember that the peak of warheads by the US and the Soviet Union in 1967 was over 40,000 during the Cold War. Then START 2, just before Bush left office, Clinton came in January 20th, 1993. 2 weeks before, START 2 was signed, which banned merged ICBMs, ratified by the US in 96 and Russia in 2000. But then the Russians withdrew, and the US withdrew from the ABM Treaty. And I'm going over this kind of. Any questions about this?
What's the definition of deployed?
Of what?
Deployed.
Deployed is physically in the ground, able to be used. And then things stood still from the latter part of the 20th century into the 21st century. When Obama came in 2009, Obama, when he was president, there was a replacement process, at least nominally. One of Putin's deputies, Medvedev, became president, although he had no power. Power was totally Putin's power. Putin became the prime minister, but Putin allowed Obama and Medvedev to sign the New START Treaty, April 8th, 2010 in Prague. And this agreement this agreement expires in February next year, 1 year from today. So this, the follow-up to START 1, it limits the number of deployed warheads to 1,550. Great reductions in the numbers of warheads. And the number of deployed and non-deployed ICBM and SLBM launchers and heavy bombers to 800. Includes non-deployed. That means that those in storage. For the first time they would be in storage, though very difficult to verify the number of stored Russian weapons, because they don't allow you to count them. Allow for satellite, remote monitoring, and 18 on-site inspections per year for treaty verification. This was the toughest set of verification measures in an arms control agreement. You also might see another term, National Technical Means, NTM. That would be any means that the US and the Russians have to verify the agreement of the other side. So this is how we got from SALT one, to the New START treaty. And now your question is, what do we do about this New START treaty? It's going to expire in 1 year. And should we renew it? Should we expand it? Should we get the Chinese involved, anybody else involved? What's in the US interest and so forth? I think that's it, our time.